Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. Okay, so we are going to start the discussion around merge sort. So I believe anybody who is going to start learning merge sort must know about what is sorting. If you don't know about sorting, then I can explain sorting in kind of like one line. Sorting is not just arranging your data in ascending order, descending order. It's not sorting. Sorting is like rearranging your data in any specific permutation that we want. Like that's sorting. And anybody who is willing to learn merge sort must have at least heard about basic sorting algorithms like bubble sort, selection sort, and insertion sort. If you don't know about bubble sort, selection sort, and insertion sort, it's not a prerequisite to learn merge sort, but it's recommended that you should have some knowledge there so that you know at least about basic sorting algorithms that are not that efficient, but yes, case to case specificity basis, they are really very good. Okay. But today we are going to learn about merge sort. To be very honest, merge sort is one of the most important sorting algorithms. Merge sort not only gives us a new sorting technique, but also opens the gate of a specific kind of paradigm of problems called as divide and conquer problems. We're going to talk about that. Based on merge sort, like few questions are very specific and can be solved with merge sort very easily. There are other ways also to solve them. But merge sort gives us a very, I would say, impressive way to solve them. The analysis of merge sort is really very important, I believe. If you talk about me with my experience, I once interviewed for Bloomberg, and the time complexity analysis of merge sort was asked in very much in depth, right? So merge sort is something that you definitely don't want to miss. And if you want to be a good programmer. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our system design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. If you want to be a software engineer, these foundational algorithms are going to give a very, I would say, strong boost to your overall software engineering career, because you see how a very basic problem is getting solved, right? I'm not going to teach you merge sort, just like what is merge sort and what are the steps of merge sort. I'm not going to teach you merge sort like that. We are going to take a specific problem. We'll first of all solve that problem, and then we'll try to generalize that problem. And then step by step, we will move to a solution which will eventually lead to something like merge sort. Okay. So we're going to start about merge sort. But before we start with merge sort, we would like to discuss one specific question. Okay. I'm not sure if you have already learned about this question or not, or if you have ever heard about this question or not, but I believe it's very fundamental and it's very, very important. Okay. So let's say, given two sorted arrays of different sizes, combine them such that the combined array is also sorted. So what do I mean when I say combined array should be also sorted? Let's just take an example in order to understand this. So let's say you are given an array A, which is something like 1, 5, 7, 10. And let's say you are given an array B that is like 2, 3, 9, 12, 16. Right? Something like this is already, let's say, given to you. Okay. Now, your expected output, this is the input. This is the input given to us. What's the expected output? The output expected is kind of like a new array C, such that it has the data of both the arrays combined. It has the data of both the arrays combined and in sorted fashion. So if you see this, the final result, the final result is also sorted. So we want the final output to be sorted. We don't want it unsorted, right? We don't want to combine them one after the other. We want to combine both the arrays such that the final result should have data from both the arrays and it should be sorted. This problem is a lot of time also called as, or you might see a lot of websites referring this problem as merge two sorted arrays. Okay, merge two sorted arrays. We are going to first of all analyze this problem. We are going to first of all solve this problem, and then only we are going to move forward with the discussion. Let me tell you about some constraints. So as I said, the size of both the arrays will be different. So let's assume the size of the first array is n and size of the second array is m, right? Let's assume the size of the first array is n and the size of the second array is m. And we can say n and m can be as big as 10 raised to the power, let's say 7, and greater than or equal to 1. Okay. These are the constraints. So constraints are pretty tight. Okay. uh, we need to kind of like solve this question in very optimized fashion. Okay, cool. Now, how can we solve the question? How can we solve the question? So I always believe that at any point of time, if something is quite new to you, if let's say this problem is new to you, then the first thing that you should do is at least try to think about the brute force. Now, what will be the brute force? Just think about it. Somebody is asking you to combine two arrays and return you the final result in sorted fashion, right? So what we can say is, let's just follow the expected steps in the question. Okay, that is combine one array after the other, combine one array after the other, and then sort them, right? So how can we combine one array after other? How can we combine one array after other? We know that the array A is of size n, array B is of size m. So our resultant C array, what will be the size of the resultant C array? C array is the one which is going to have the combined data of A and B. So the resultant C array will be of n plus m length, right? So what we can do, we can create a new array of size n plus m. We will create a new array of size n plus m. We will copy the data of array A first and then array B, and then sort the array C, and then sort the array C. So let me tell you what I'm trying to say. Let me explain what I'm trying to say. So let's say this is your given, this is your given input, right? This is your given input. So what I'm trying to say is create a new array C. The array C should be of size n plus m, right? So here it's, let's say 4, here it's 5, so it should be of size 9. Okay, then first of all, copy all the elements of A inside C. So 1, 5, 7, 10. And then one by one copy all the elements of B. So 2, 3, 9, 12, 16. It's easy, right? You have to just place all the elements of A first, then you have to place all the elements of B. Okay, and then sort the array C, right? If you use a sorting algorithm like insertion sort, selection sort, bubble sort, right? If we use selection, insertion, bubble, if you use these kind of sorting algorithms, then if the length of the array is, let's say n, then these algorithms in the worst case take n square time. Here we have the length of the array is n plus m. So the complexity here will be what? Order of n plus m square, right? And maybe you can use some alternative sorting algorithms. Maybe we can use something like quick sort, right? Or let's say heap sort, right? There is merge sort also that you can use. We are going to learn about merge sort later. But like even merge sort, if you will use, what is merge sort? If you don't know, don't worry. But even merge sort we can use. Then all of these sorting algorithms on an average works in n log n. If the length of the array is n, then they work in n log n. So our array length is order of n plus m. So our complexity will be n plus m log n plus m. Okay. So definitely using these algorithms is going to be better than using this. But we have solved the problem in order of n plus m log n plus m time, right? Why this complexity n plus m log n plus m? Because let's say heap sort, quick sort, merge sort, all of these sorting algorithm, if the length of the array is n, then they work in n log n. Here instead of n, we have n plus m. Instead of n, we have n plus m. So we will replace n plus m everywhere. So this will be n plus m log n plus m, right? So this is like a brute force way. And that's what we said, right? I said that combine one array after the other. So here you can see I combined one array after the other, and then I sorted them. So here you can see we will sort the array. So sorting the array will look like this: 1, 2, 3, 5, 7, 9, 10, 12, 16, I guess, if I have not missed any element, right? So this will be the most brute force approach to think. When I talk about brute force, I don't mean like the worst possible case. At least when I say brute force, that then I mean that if we don't apply any specific algorithm, if we don't apply any specific trick or anything, then what's the okayish thing that we can do? Because in the brute force, you can think that, okay, there are sorting algorithm that works even worse than bubble sort or selection sort. So you can even use that, but we are not going to take that. We are not that dumb, right? Okay. So this is like the first approach that you can use in order to merge two sorted arrays. Now the question arises is, how can we optimize? How can we optimize? In order to optimize, we need to think in a bit smart way, I believe. We need to think in a bit smart way. What do we want? We want both the arrays combined, and we want the final combined output to be sorted. This is our expectation, right? Now, you guys tell me that if we try to figure out the smallest element of the final output, if we try to figure out the smallest element of the final output, for example, what will be the element? What will be the element? Right? Now, can I say, if we have this also sorted, this array A also sorted, I have array B also sorted, then the final element of the sorted array, first smallest element of the final output, that is the final sorted array, will be one of the elements, one of the smallest element from the given two arrays. So it will be one of the smallest elements of the given arrays, right? That is, the smallest element will be what? Who is the best candidate? If we have not done any algorithmic technique or like no code, nothing, we just have an array A, we just have an array B, we can definitely draw a conclusion that in the final output, the smallest element will be either the smallest element of A or the smallest element of B. Can I say that? One of the two elements, these are the only two candidates. One of these two candidates is going to be the smallest element of the final output, right? Okay. Let me again copy this. Okay. Now let's say if we have two candidates and we want to find the smallest one, we can just calculate. So C of 0 will be what? Minimum of A of 0 comma B of 0. That is A of 0, that is 1. Okay. So we can say that element 1 is done. We are done with this element. We do not need to consider it later. Okay. We do not need to consider this element 1. Why? Because we have considered this. It is the smallest element, so it will go to the 0th index of the final array. Okay. Now I ask you guys one more question. Okay. In the final output, which element will be the second smallest? Previously I asked that which element will be the smallest of the output. Now I am asking which element will be the second smallest in the output. That is, I am asking for which element will be placed at C of 1, right? We already decided that on the 0th index of the final output, the minimum element will go from both the arrays. Now I'm asking for the second smallest. Who are the two best candidates of the second smallest? The two candidates are first, the element that didn't become the smallest element. Whom I am talking about? I'm saying the element that didn't become the smallest element. So for the smallest element, 1 and 2 fought and 1 won. So who lost? 2. So 2 is one of the candidates to become the second smallest. Okay. 2 is one of the candidates to become the second smallest. That's why I'm not saying that it's B of 0 or A of 0. No. I'm writing a general case that whosoever won the fight to become the smallest, we will be having one winner. So this is one was winner, but we'll be having one loser. So the element that didn't become the smallest, that is 2. That's the first candidate to become the smallest, second smallest. And second, what will be the second element to become the, I would say, second smallest element is the smallest element of remaining array A. In our case, because 1 is considered, we will say that 1 is now not even present because 1 is gone to C, right? Now we are left with 5, 7, 10 here and 2, 3, 9, 12, 16 here. So one element will be coming who lost and one element will be coming from this new array because now we don't need to consider 1. So 5, 7, 10 is kind of like a new array. We'll see how we will manipulate and mimic this new array, but the first or the smallest element of this new array. So 2 and 5 are the two best candidates to become the second smallest. And how will you calculate this? That is C of 1 will be equal to minimum of A of 1 comma B of 0. So in our case it will be B of 0. That is 2. Can I say that? Right? So this is the approach that we are going to take. Once this is also done, once this thing is also done, now we can say 1 is also completed, like 1 is also used, 2 is also used. Now we are left with what? Now we are left with this array and this array. Who will be the candidate to become the third smallest? I will say the element that lost the fight to become the second smallest, that is 5, and the element which is present in the new first smallest element in the new array, that is 3, and so on and so forth. This is how we can move forward one by one, and we can say in every iteration of this logic, we can eliminate not even at least, but we'll say we can eliminate exact one element by just a comparison. By just a comparison. Can I say that? So we can say, so a comparison is a constant time operation. That means the complexity of this particular algorithm looks like order of total number of elements, and total number of elements are n plus m. In the first array, the elements are n. In the second array, elements are m. In every iteration, you are eliminating one element. So how many iterations will be there? There will be number of iterations will be equal to the total number of available elements. How many total available elements are there? N plus m. And each iteration is a constant time operation because comparison is constant. So complexity will be order of n plus m in terms of time. This is in terms of time. And in terms of space, it will be order of 1. In terms of space, it will be order of 1. So we have solved our problem in a better complexity than the previous complexities that we saw, right? So now the question arises is, we know the logic, how can we implement it? Okay. So when I say that we choose one of the element to be the smallest element of the final array, and then we forget about that, then technically, if you will try to remove that element altogether from the array by using any method of your corresponding programming language, for example, if you try to, like after the first iteration, reduce it to 5, 7, 10, this is not going to be very efficient. Why? Because removing an element from the start of the array is going to create like it's going to take order of n time, right? Because in most of, if let's say it's create a completely new array of lesser size, then it's going to take up extra space also, and it will take order of n time also. And even if it doesn't like make an extra array, then also it is going to copy all the elements to the previous index. So 5 comes here, 7 comes here, 10 comes here, and this will be a dummy value. So in both of the cases, removing an element altogether is not going to be very efficient. It's going to take order of n in every iteration. But as we discussed, we just want to do a comparison in constant time. So every elimination that we want to do must be in constant time. Okay. So what we can say is, we can here use a technique called as two pointers. Right. We can here use a technique called as two pointers. Two pointers doesn't always mean like you have to take two pointers and iterate using them. So I'll just explain it in a nutshell. Two pointers is a technique in which we try to, I would say, eliminate some elements by just reducing their origin. Like, for example, if let's say I keep a pointer here, I keep a pointer here, I'll say that I'm going to consider, let's say, let's write the pointer I and let's write the pointer j. I'm going to consider the array A starting from index I till n minus 1 and j starting from index j till m minus 1. If after some time we have to eliminate some elements from, let's say, array B, and let's say I put j here, then as I said, starting from index j ending at m minus 1. So we are not going to consider these two elements. So we don't have to like eventually delete them, but we can just define a space that, okay, inside this region, all the elements we are going to consider, rest of the elements we are not going to consider. So generally two pointer techniques are helpful when we have data arranged in a specific fashion, so that in each iteration we can move the pointers and like eliminate some data or reduce the region of consideration, etc. So let's just see what we are trying to say here. I'm saying we'll create a new array C. This array will be of size, of course, n plus m. Now we are talking about the smallest element of C. Right, we are talking about the smallest element, which will be the smallest element of C. We will compare A of I with B of j. I am saying we are considering array A from index I to n minus 1 and B from index j to m minus 1. So currently I is at 0, j is at 0. We will say if A of I if A of I is less than B of J, if A of I is less than B of J, we will say C of K is equals to A of I. So we'll keep a pointer K here also so that we can iterate on array C and say if A of I is less than B of J, then on C of K, I will put A of I. So what is A of I? 1. I will put 1 here. Then I'll say K plus plus and I plus plus. That is, I will move K forward because this region is done, and I'll move I forward because this element is also done. So now we are going to consider array from I to n minus 1. So I comes at index 1. J is still at index 0. We are going to again compare. If A of I is less than B of J, this time no. So we'll say if B of J is less than A of I, we'll say C of K is equals to B of J, then J plus plus K plus plus. So let's see. A of I is 5, B of J is 2, 2 is less than 5. So this time 2 won. So we are going to put a value 2 and we will do J plus plus and we will do K plus plus. Now again we are going to compare A of I with B of J. This time again B of J is less. So we'll put C of K is equals to B of J and then J plus plus K plus plus. Now A of I is less than B of J because 5 is less than 9. So we'll put a value 5 here and I plus plus K plus plus. 7 and 9, A of I is again less than B of J. So 7 here, I plus plus and K plus plus, sorry, K plus plus. Now B of J is less than A of I. So we put 9 here and then J plus plus and then K plus plus. A of I is less than B of J. So again 10 here. We do I plus plus and we do K plus plus. Okay. 1 second. Okay, cool. Now you can see array A is exhausted. The moment array A is exhausted, we know that all these elements are done. But maybe array A is exhausted, but B might not be exhausted. And you can see B still has got 2 elements. Now we can say that if array A has been exhausted, then the remaining elements of B were definitely greater than all the elements of array A. So we can just one by one place them here. So we can put a separate loop, like once array A is done, array A is completed. We are not going to do this comparison because we don't have any element to compare. What we will do, we will just one by one put all the remaining elements inside K. So here we have 12, we'll put 12, then K plus plus, J plus plus, then we put 16, sorry, J plus plus, K plus plus, and done. And this thing can happen vice versa also. Like maybe array B can get exhausted first and you might have still some elements left in A. Then again, what you will do, you will just copy the remaining elements of A inside array C. This is how you implement your merging of two sorted arrays, right? So we'll just put a note that if one of the arrays get exhausted, then all the remaining elements of the other array can be just directly inserted. That's it. Can be just directly inserted. What will be the time complexity? You can see we just did what? In each iteration, we just did comparison. So order of n plus m, and we are not taking any extra space. So order of 1. If we do not consider the space of the output array. This is our algorithm to merge two sorted arrays. So how can be the coding implementation done? We'll say function merge. Okay. I'm going to write a code that is going to be almost language agnostic. So whatever language you want to implement it in, you can do it. We are going to get an array A and an array B. What we are going to do, we are going to get an array, let's say, let an array C is equals to array of size n plus m. And what is n plus m? Let's say let n is equals to a dot length and let m is equals to b dot length. Okay, we're going to create an array C of length n plus m, and we are going to get a variable I and a j. These are going to be our 2 pointers, and one variable k also, that is going to iterate over array C. So I will iterate on A, j will iterate on B, and k will iterate on C. And we say that while I is less than or equal to n and j is less than or equal to m, we'll check if a of I is less than b of j, then c of k is equals to a of I, then I plus plus k plus plus, else c of k is equals to b of j, then j plus plus, sorry, j plus plus and k plus plus. Okay, this loop is going to compare all the elements. Now if array A is exhausted first and few elements are left in B. If let's say we exhausted array A first and few elements are still left in B. If few elements are still left in B, can I say this condition that j is less than b dot, or let's say j is less than m? Do you think this condition will hold true? If B has some elements left, then j will be less than m, right? Because m is b dot length. If this condition holds true, so we'll say while. So while this condition holds true, we'll say c of k is equals to b of j, and without any comparison, just do j plus plus and k plus plus. Right? And one more thing that I did by mistake, I guess. This should not be equal. This should be less than n. Because we can only go to a dot length minus 1, right? So this should be less than n and less than m. Okay, cool. Now this condition will be hold true if A is exhausted and some elements are left in B, but maybe some elements are not left in B. Maybe if array B is exhausted and few elements are left in A. If this will be the case, then this condition will not be hold true. This loop will be skipped. And if let's say this condition is what? I is less than n. If I is less than n, that means few elements of A are still left. So while few elements of A are still left, we'll say C of k is equals to A of I plus plus, k plus plus. And that's it. From here, we are going to return C, the array C. This is going to be the full implementation. Right. What will be the complexity of the algorithm? The time complexity of the algorithm is going to be order of n plus m. And space complexity, I'm specifically writing as order of 1 without considering output space. Okay. Maybe somebody can argue on that. So we'll say if you want to consider output space, write it n plus m. We are not considering output space as in the part of the complexity of the algorithm. So it's going to be order of 1. Okay. So these two are just the extra conditions that we have to put for the exhaustion case, that if array A is exhausted, that means no elements is left in array A, but maybe some elements are left in array B. If some elements are left in array B, then this condition will hold true. So while this condition is true, just keep copying the elements. Or maybe B was exhausted, A is having some elements left, then this condition will hold true. At last, we are going to return C. If you try to execute it, let's say A is equals to 1, 5, 7, 10. Let B is equals to 9, 12, 16. We'll say console.log merge A, B. Merge A, B. And we can say node merge to sorted arrays.js. And you can see the final output is 1, 2, 3, 5, 7, 9, 10, 12, 16. So this is the sorted output, right? So I'll paste the output here. Okay, this will be the output. So we have successfully implemented the function merge to sorted arrays.